Forwards, backwards, forwards, backwards. Why are some chemical reactions reversible and not others? What is special about reversible reactions? How can I make this chemical reaction go backwards just by squashing it? And which of these reactions is reversible and why? Keep watching to find out. Now, we're going to start right at the beginning by remembering that chemical reactions are all about breaking and making bonds. I know that's obvious, but we need to remember that breaking bonds needs energy, which must come into our molecules from somewhere. Perhaps photons will change the bonding in a molecule, or one molecule will just slam into another and break apart. And making bonds means the atoms have to lose some energy. Maybe the energy will be lost by bumping into another molecule or getting trapped in a sticky electron cloud and losing the energy by vibrations. In short, breaking and making bonds is all about energy arriving and leaving. So, understanding what's different about reversible and non-reversible reactions means learning a bit of thermodynamics. But don't worry, we're going to use a super simple model because that's all we need. Now, there are 4 simple principles in our model, which are: 1. Energy always goes everywhere that it can. That's because it's stupid and doesn't know where it should be going. And this is a fundamental feature of our universe, at least until we start thinking of galaxies as small things. 2. There are many ways we can talk about what energy is, but today we're just going to focus on particles. In other words, atoms and molecules. It's partly to keep things simple, but mostly because, as I said before, that's all we need. Sometimes we're going to be focusing on molecules and sometimes on the atoms that make the molecules. When they move, they have kinetic energy, and the faster they move, the more kinetic energy they have, and vice versa. And temperature is the average kinetic energy of all of those molecules, whether they're flying through space as gases or vibrating in a solid. 3. We're going to talk about a balloon filled with molecules, and we're going to call that whole thing our system. Sometimes the big molecules break up to make smaller ones, and sometimes the small ones come together to make bigger molecules. And because we're mostly looking at gases today, we're sticking them in a balloon so they're free to move around without getting lost. That means the molecules can't get in or out of the balloon, but heat can. Heat transfers inside and out because the gas molecules hitting the balloon change how the balloon molecules vibrate, and those vibrations change the kinetic energy of the gas on the other side, and the heat is transferred. And that means we have a closed system at constant pressure. And 4, our balloon is going to start and finish the reaction at the same temperature as its surroundings. That means it'll be at thermal equilibrium at the start and then again at the finish. And thermal equilibrium means heat energy is going in at the same rate as it's coming out. In the middle of the reaction, our balloon might get very hot or very cold, but we're not worrying about that. And just a quick extra note, for those of you that have already studied some thermodynamics, I'm using the word energy here in a different sense to most textbooks. We need to start with these concepts and rules because they are essential to understanding how energy is going to scatter outside and inside our system. And in fact, it was this understanding that inspired Henri Le Chatelier to explain how reversible reactions work. He was the one who spotted how this simple equation derived by Josiah Gibbs could explain everything about reversible reactions. So let's take a look, and don't forget, we're going to keep everything really simple. So here's the equation again, and it tells us how much energy is left over after everything that must be done in the reaction has been done. It's actually a measure of how much energy will be set free after the reaction has finished, and that's why we call it free energy. And you probably know this, but that delta symbol means the difference. In this case, the difference between the amount of free energy before the reaction and the amount after. So, if this extra energy has been set free and it's scattered as much as it can, it's gone out of our system. So we've effectively lost it. And if we've lost it, we're going to write this amount with a minus sign. Just like when you spend money from your bank account, it makes sense to write it as a negative number. So if delta G is negative, energy has scattered and gone everywhere that it can. And that means our reaction is going to work because scattering everywhere it can is what energy does. And conversely, if delta G is positive, it means that somehow extra energy has to come out from the universe and descatter into our balloon. But why would it do that when there's the rest of the universe to play in? Remember, the inside and outside of the balloon are the same temperature, so it's not because the outside is hotter. Very simply, energy doesn't know we want it to go inside the balloon. So if our calculation gives us a positive value for delta G, it means our reaction won't work like that. And it actually means we've just written our reaction the wrong way around. Now, biology does write reactions with a positive delta G quite often, but that's because they're writing imaginary reactions. And that's okay because they're doing biology, not chemistry, and it's a kind of shorthand for one part of a whole network of reactions where the whole process has a negative delta G. Now let's take a look at the right side of the equal sign. Here we have two terms that tell us what the value of delta G is going to be. Starting with delta H, this is the change of energy that we can measure with a thermometer, in other words, heat. And don't forget, heat can leave our balloon, and if it does that, we're going to make delta H a negative number. And if heat energy ends up going from the outside in, it's going to be a positive number. And a quick aside, for those of you that know the difference, I'm going to be calling enthalpy heat through most of this video. If you don't know what enthalpy is, don't worry for now, but we'll see it again later. So, the obvious point is that if delta H is negative, it's going to make delta G more negative and vice versa. Now let's move to the second term, and we'll start with delta S. This stands for the difference in entropy before and after the reaction. Simply put, entropy is a measure of the freedom of energy to scatter within our molecules. Scatteredness is the word I use, by the way, because it describes entropy better than any other word I can think of. Oh, and it begins with an S, which is either pure coincidence or pure genius. I'll leave you to decide that for yourselves. Crucially, this scattered energy doesn't show up on a thermometer. There are many ways it can hide in a molecule, but we're going to focus on the big obvious one, which is the collection of molecules having more freedom to move than they had before. For example, when big molecules have broken into lots of smaller ones, but the pieces aren't moving much faster. And once they've scattered, going everywhere that they can, they're just not likely to reorganize themselves back into big molecules. Because they're stupid and don't know that we want them to come together. But crucially, scatteredness is not a measure of an amount of energy. So all we do is multiply the new scatteredness of the molecules by the average amount of kinetic energy each molecule has, which is temperature. And now we have how much energy has been scattered within our system compared with before the reaction. And you can see the minus sign here, which means that the more positive the change of entropy is, the more negative delta G is going to be. And that shouldn't be a surprise because entropy is about scatteredness, and we've already said that delta G is all about energy being scattered and set free. Because that, remember, is what energy does. So, in summary, delta G is how much energy has been set free and scattered after all the essential processes of doing the reaction. Delta H is how much energy has been scattered as heat. Delta S is the new scatteredness of our atoms, and that, combined with temperature, tells us how much energy has been scattered inside our molecules. That's the explanation of the equation, so now let's put it all together. If a reaction is exothermic, heat will spread outside the balloon into the rest of the universe. That's what energy does, so that means our reaction is more likely to happen. But it also means that atoms have formed new bonds. They've lost their energy and now they're stuck together. If it's endothermic, however, energy as heat has to somehow come out of the universe and go into our system of atoms. But why would it do that? It doesn't know it's supposed to be going in there. But energy does move around randomly, so sometimes a little extra will go into our balloon. And once it's there, it might break up a molecule and end up scattered around on the pieces, hidden from our thermometers. Breaking up molecules scatters the pieces in our system, and smaller molecule scattering is simply more likely to happen than them organizing themselves back into bigger molecules. And the more we shake them, the more likely they're going to scatter, and the less likely they are to organize themselves. And that shaking is temperature. So, if our reaction releases heat and scatters molecules, it will definitely happen because statistically that's what energy and molecules do. But if heat has to come out of our surroundings and go into our molecules, and the molecules have to organize themselves into bigger, fewer molecules, then it definitely won't happen. And that actually means we've just written our equation the wrong way round. But now, what if the heat and the entropy disagree? For example, what if the heat spreads out, but the molecules have to come together to make fewer larger molecules? Or what if the molecules spread out, but extra heat has to go into our system from outside? Well, then we get a fight. And it's temperature that decides which one's stronger. And this makes sense. The higher the temperature is, the more likely it is for the larger molecules to get smashed into smaller pieces, or simply shake themselves apart. So if a reaction is scattering atoms, higher temperatures will help that happen. And of course, the opposite situation applies to lower temperatures. When there's less shaking and smashing, it's easier for larger molecules to form and stay in one piece. So, now we can understand what makes a reaction reversible. It's reversible because going in one direction is favoured by heat, while the other direction is favoured by entropy. Okay, so now let's take a look at that syringe full of toxic nitrogen dioxide. But before we do, I just want to tell you this video is produced at Kyushu University, which is one of the top universities in Japan. We've got science and engineering courses in English, and it's a great alternative in these uncertain times. And of course, there's a link in the description. Okay, so now let's take a look at that syringe filled with toxic nitrogen dioxide. Here's the equation, and we can see that in this direction, the reaction involves atoms getting organized from two molecules into only one. That's a big clue that entropy is going to be negative for this reaction, and indeed it is. Next, since we're making a bond here, we're expecting that heat is going to be negative for this reaction, and it is. So heat is negative, meaning the reaction is exothermic, but entropy is also negative, so the reaction must be reversible. And of course, if we write the reaction the other way round, everything is in reverse. And all of that leads to the special behavior we see for reversible reactions. The two reactions make a dynamic equilibrium where both are happening at the same time. And I've made a video showing exactly how dynamic equilibria work, so check it out if you want to know more. Now, I've done an experiment to show exactly how temperature affects the equilibrium ratios, and now you should at least have an idea of how that works. But let's stop talking about forwards and backwards, because we can always write reversible reactions either way round. So instead, let's talk about the enthalpically favoured reaction and the entropically favoured reaction. And don't forget that the effects of entropy are multiplied by temperature. So here is our reaction mixture inside this syringe. NO2 is dark brown, N2O4 is colourless, and the colour of this syringe would tell us we have a mixture of both gases if we measured it carefully. So, if we make the mixture cold, the exothermic, enthalpically favoured reaction is more important. That's because it's easier for the heat to leave the syringe and not come back, and also because it's easier for atoms to stay together in large molecules. So, more of the atoms get trapped as N2O4 molecules, and with less NO2, the colour is paler than it would be with no reaction. But now, if we make the mixture hot, we make the entropically favoured reaction more important. The high temperature provides more kinetic energy for breaking up the N2O4 molecules and scattering the atoms as smaller NO2 molecules. And more NO2 means the mixture gets darker. And I know I just said I shouldn't say this, but forwards, backwards, forwards, backwards. It's too much fun. And as a bonus, we can also see how the dynamic equilibrium resists pressure changes. The mixture starts as a brown colour because NO2 is brown, but it should go much darker as I compress it into a much smaller volume. But it doesn't, it stays the same colour all the way. That's because the higher partial pressure of NO2 means that the molecules collide more often and make more colourless N2O4. And in this reaction, there's an extra step where N2O4 condenses into a liquid, which is why the glass goes misty. This condensation removes N2O4 from the gas phase, driving the equilibrium even more towards the right. So these two equilibria reduce the amount of NO2 even further. And when I reduce the pressure, the N2O4 evaporates back into the gas phase, and with the lower partial pressure of NO2, it's less likely for N2O4 molecules to form. So we get more brown NO2 gas, and that means the colour keeps its intensity, even though there is 5 times more volume for it to fill. I love this demonstration. I think it's so cool. And if you like it too, and click the like button, it'll help me make more videos. Thanks. Okay, so first up, dynamite, which we're going to simplify to just trinitrotoluene. No surprise that it's very exothermic, so heat says the reaction goes forward. But what about the entropy? Well, 2 moles of solid become 20 moles of gas, so not only are we massively increasing the number of molecules, we're also getting atoms out of a solid and setting them free as a gas. So, final verdict. Heat says forwards, entropy says forwards, so it only goes forwards at any temperature. It is not reversible, and that's not going to surprise anyone. But how about this one? The wood fire. Trees make wood from carbon dioxide and water, right? And when we burn it, it goes back to being carbon dioxide and water, doesn't it? Well, let's take a closer look. The chemistry of wood is quite complex, so let's simplify it by remembering that it's mostly cellulose. And cellulose is a polymer of glucose, so we'll look at glucose as a simplification of wood, and it won't be far off. Firstly, we already know that burning wood is exothermic, so heat says this reaction will go forwards. When we look at the reaction, we've got 1 molecule in the solid phase and 6 molecules in the gas phase, turning into 6 gas phase molecules and 6 liquid phase molecules. We have 6 gas phase molecules on the left and 6 on the right, so we'd need experimental data to decide which of those has a higher entropy, but they're not going to be very different. So let's skip over those for the moment. If we look at the other components, we're starting with atoms in one big solid molecule and scattering them as 6 water molecules in the liquid phase. Those water molecules are free to move around even if they're not as free as gases, so we've definitely got a big increase in entropy there. So, final verdict? Heat says forward and entropy says forward, so this reaction goes forwards at all temperatures. It is not reversible, which means you will never see wood spontaneously forming from carbon dioxide and water. But what about trees making wood from carbon dioxide and water? Well, there are 2 things to remember. Firstly, plants don't make cellulose in one reaction, they need a whole network of separate reactions to build the cellulose bit by bit. And secondly, plants need a flow of energy from the sun to drive this system. The carbon dioxide and water will never make cellulose in a closed system. And since this is a thermodynamic limitation, there is nothing enzymes can do about it either. Okay, so on to our last one. That ain't reversible. Is it? These rockets use the reaction between hydrogen and oxygen, which as we all know goes bang and releases a lot of heat. So heat is definitely saying this reaction will go forwards. But what about entropy? Well, here we can see that 3 molecules of gas come together to make only 2 molecules of water liquid. The atoms have to somehow get organized to do that, so it's going to be a very rare occurrence. So heat says the reaction will go forwards, but entropy says it will only work backwards. And that means this scary looking reaction is actually reversible. Which can't be right. Can it? Well, I'm cheating a little bit because this is not a closed system. In fact, it's an example of driving an equilibrium by removing the product, water, from the reaction. Hydrogen and oxygen reacting to make water is the enthalpically favoured reaction. And when the atoms make water, they lose so much energy, they get stuck that way. So the back reaction is going to be so slow at room temperature, it does not significantly occur. But at very high temperatures, the entropically favoured reaction becomes important enough to make the reaction go significantly backwards. This is because the water molecules are getting slammed so hard, it's easier for the atoms to make more smaller hydrogen and oxygen molecules. In fact, the reversibility of the hydrogen-oxygen reaction is what makes hydrogen energy a potential solution for energy storage. So we can use renewable or nuclear energy to split water back into hydrogen and oxygen, store the energy as hydrogen, and get it back later with low carbon emissions. The engineering still has a way to go, but we already have hydrogen-powered buses and trains right now, and in my opinion, it's still one of the best candidates for replacing fossil fuels and combating the disasters caused by global heating. So, there you go. Now you know what it is that decides whether a reaction is or is not reversible. Or you could just guess. Because if you guess a reaction's reversible, you'll be right most of the time. Because most reactions are reversible. In fact, the reason we usually use single arrows is because either the back reaction is too insignificant, or we just can't be bothered to draw 2 arrows. So, do you understand reversible reactions better now? Do you have any examples of a surprising reversible reaction? I love reading your comments, so please let me know, and I'll see you next time.